Hello guys, welcome back to my channel. As you know, I am Likit. So today I am going to be explaining a topic from the subject Automata Theory and Compiler Design whose subject code is 21CS51. So let's get on. So non-deterministic finite automata NFA. So let's get on with the introduction. A non-deterministic finite automaton NFA has the power to be in several states at once. This ability is often referred as an ability to guess something about its input. For instance, when the automaton is used to search for certain sequence of characters, example keywords, in a long text string, it is helpful to guess that we are at the beginning of one of those strings and use the sequence of states to know nothing but check that the string appears character by character. So, definition of non-deterministic finite automata. Now let us introduce the formal notions associated with non-deterministic finite automata. The, the differences between DFAs and NFAs will be pointed out as we do. An NFA is represented essentially like a DFA. A is equal to Q, comma, summation, comma, delta, comma, Q naught, comma, F, where Q is a finite set of states and summation is a finite set of input symbols. And Q naught is a member of Q and is the start state. And F is a subset of Q is a set of final or accepting states. Delta being the transition function is a function that takes a state in Q and an input symbol in summation as arguments and returns a subset of Q. Notice that the only difference between an NFA and DFA is in the type of value that delta returns. A set of states in case of an NFA and a single state in case of a DFA. Example. So the start state. In this case, in this example, Q0 is our start state and Q2 is our end state, which is indicated by our final state, which is indicated by two circles. So this is an NFA accepting all strings that end in zero. So we'll be taking three states with the start state having a self loop of 0, 1 and sending 0 to Q1 and Q1 sending 1 as 1 to Q2. So the NFA of figure 2.9 can be specified formally as Q contains Q0, Q1, Q2. These are the states 0, 1, then followed by delta, then Q0 and Q2, where the transition function of delta is given by the transition table. This is our transition table. So we know that Q0 of 0, 1. So Q0 points to 0. So in this example, the transition table is given by like if Q1, so wherever Q0 is pointing sending 0, that will be considered as Q0 of 0. So Q0 goes from 0, so Q0 of 0 goes to Q0 as well as Q1. So there it is Q0, Q1. Then we have from Q0, there is a self loop to 1 itself, of 1 to itself. So it will be Q0 of 1 becomes Q0. Then we have Q naught of 0. So Q naught of 0 means Q naught of 0. It's sorry, not Q naught. Q1 of 0 is 5 because there is no, because from Q1 there's 1 is not going to anywhere, or 0 is not going to any state or itself. So then we have Q1 which is pointing to Q2, Q1 of 1 which is pointing to Q2. Then we have Q2 which is the final state, which it basically does not have 0 as well as 1, so the values will be 5. This is a transition table for an NFA that accepts all strings ending in 0, 1. So you can notice that the transition table can be used to specify the transition function for an NFA as well as for a DFA. The only difference is that each entry in the table for the NFA is a set. Even if it is a singleton, has only one member. Also notice that when there is no transition at all from a given state on a given input symbol, the proper entry is 5, the empty set, as we have for Q1 of 0, Q2 of 0, as well as Q2 of 1. As we have, there is no transition, we signified with a 5, which represents empty set. Okay, the language of an NFA. An NFA accepts a string W if it is possible to make any sequence of choices of next state while reading the characters of W and go from the start state to any accepting state. The fact that other choices using the input symbols of W lead to a non-accepting state or do not lead to any state at all. That is, the sequence of states dice does not prevent W from being accepted by the NFA as a whole. Formally, if A is equal to Q comma summation comma delta comma Q naught comma F is an NFA, the language of A will be W of delta power Q naught comma W, which is a subset of F is not equal to 5, where F is not equal to 5. That is, language of A is a set of strings W in summation star such that delta power Q naught comma W contains at least one accepting state. Then equivalence of deterministic and non-deterministic finite automata. Although there are many languages for which an NFA is easier to construct than a DFA, such as the language of strings that end in 01, it is a surprising fact that can be described by some NFA can also be described by some DFA. Moreover, the DFA in practice has about as many states as the NFA, although it often has more transitions. In the worst case, however, the smallest DFA can have 2 to the power n states, while the smallest NFA for the same language has only n states. The proof that DFAs can do whatever NFAs can do involves an important construction called the subset construction because it involves constructing all subsets of the set of states of the NFA. So now let's look at a bad case for the subset construction. It is quite common in practice for the DFA to have roughly the same number of states as the NFA from which it is constructed. However, the exponential growth in the number of states is possible. All, all the 2 to the power n DFA states that we could construct from an n state NFA may turn out to be accessible. The example does not quite reach that bound, but it is an understandable way to reach 2 to the power n states in the smallest DFA that is equivalent to an n plus state NFA. So this concludes my presentation. So thank you for watching.